Fast by Friday, making performance analysis fast and easy. Brendan Gregg.
Thank you and welcome. It is my honor to keynote SRE NEXT in Tokyo 2025. What would it take to solve any computer performance issue in 5 days? I've thought about this a lot over the last few years. Some performance issues are taking a month to solve, 2 months, 6 months. It's too long. For SREs, it is even harder. What would it take to solve any computer performance issue in 5 minutes? This is very important. Imagine solving the performance of anything: operating systems, kernels, web browsers, phones, applications, websites. Imagine websites should load in the blink of an eye. Your computer should boot straight away. Phones should boot straight away. This is good for the environment. It's also good for innovation, as it rewards investment in engineering. It's good for companies, it's less compute expense, and it's good for end users. Fast by Friday is what I've been working on for a while, and it's very simple. Any computer performance issue reported on Monday should be solved by Friday or sooner. The issue is any performance analysis task, especially software and hardware evaluations. I work at Intel, and I often help with checking Intel's performance versus other hardware. And if it takes too long, the customer gets tired and may pick someone else. We need to solve performance and tune and optimize performance very quickly. Solved by Friday doesn't mean fixed. It means that the root cause of the performance issue is known. Fast by Friday is, the main thing is a thought exercise. What would it take? I'm an engineer. What would I change to be able to solve performance in 5 days? This becomes a requirement for programming language runtimes, for operating systems. It is a vision, a way of thinking, a call to action. We all need to make changes to our environments, our operating systems, to do fast and easy performance solutions. A methodology and a practical deadline. I want to understand the performance of everything in 5 days. It's also the first of 3 activities: finding the root cause or causes of a performance issue. Then there is the fixing the performance issue, and then deploying it. Usually the first task is the slowest. As I said, it can take 6 months to solve performance. Once you have a solution, the other tasks can be easy. If you can improve performance by 30% or 50%, companies will adopt that very quickly. This is also the next era in computer performance analysis. I've summarized them like this. The first era, with serial computing in the 1950s and early 1960s, there were not really software metrics. This is hardware optimizations only. Software metrics, as far as I can see, came about with multics and with time-shared operating systems including the Apollo Lunar Module Guidance Computer, which is a pioneering system that could run multiple tasks at the same time. The engineers in the 1960s that sent man to the moon knew that there could be performance issues when one computer is running multiple tasks. And they did some of the early work with identifying a system is overloaded. When the Apollo lunar module descended on the moon, there were alarms that Neil Armstrong and Buzz Aldrin had to fix, the 1202, 1204, and those alarms. These were performance issues. That's the birth of that next era of software metrics, which I would say was from about the 1960s to 2000s. Time-shared operating systems running multiple tasks or threads, and a new type of performance measurement, software metrics, where you're looking at the run queue length of the scheduler. I'm looking at disk IOPS. Also that era, I began my performance work in this era, and performance engineers were good at inference, being able to look at a few small measurements and understand the bigger picture, understand the kernel, because you couldn't measure the kernel in detail. You had to make do with whatever metrics you had. The next era, solving everything. This really began in the early 1990s with the development of dynamic instrumentation. Dynamic instrumentation did not become popular until I published my dtrace toolkit and dtrace tools in the 2000s, which saw widespread use, and now I've published many eBPF tools, and that's a diagram with many of my tools. That era is seeing everything. Open source is necessary so that we can see the software and dynamic instrumentation. We're at the point where I have published over 500 performance analysis tools, and I can solve and see, I can see everything inside a computer. Fast by Friday is about the next era. It's about solving everything, not just seeing everything. I used to work at Netflix, and a common request from my coworker was, we need tools to solve performance used by people whose name is not Brendan. I published many tools for Netflix, and they were difficult. Other engineers found them difficult to use. And so this has begun my thought of the next era of tools must be easy, usable by everyone. Solution-based tools. The problem that I'm solving with Fast by Friday is I've got expected performance improvement for computing products. Sorry. Now, with computing, you would expect each year the performance to go up. There is new hardware, there is new software, new libraries. In reality, there are many companies and sites where this is what performance looks like from one year to the next. Performance does not improve that quickly. This looks very familiar to some Netflix microservices that I worked on. The problem is that bottlenecks may not be found in time because it takes too long to analyze software. There can be not enough time to analyze new software and hardware options. At Netflix, we were running Java, and it takes time to evaluate the different JDKs, to evaluate the different compilers, Graal versus C2, to evaluate the different garbage collection algorithms. And that's just within Java. There was also Node.js and Golang. There's Linux, FreeBSD. There's so many different options, including hardware products. And regression's not solved in time. So you can imagine that you're losing performance based on the speed of analysis. Computers are getting increasingly complex. As I said, performance issues can take 6 months to solve. It's too long. I've drawn a diagram just of hardware. When I did university, I learned a computer looks like the left, but nowadays it's far more complicated. We have P cores and E cores. We have an IPU. We can have different types of memory, HBM, accelerators on the processor. So I work at Intel, so I've drawn things like QAT, IAX, AMX, DSA. Are you using them? Are they utilized? Are they helping performance, or are they not even turned on? We've got GPUs, FPGAs, TPUs, DPUs. This is just hardware. It is so much more work, much more complicated. And software is more complicated as well. We have Kubernetes, Docker, sidecars. We've got layers, abstractions. Everything is much more complicated than when I began. A common scenario at product vendors, I work at Intel, I used to work at Sun Microsystems, is you think your product may be the fastest, but you've got 1 week left before the customer will kick you out. And you have to make it fast by Friday to win the customer. So how will we do this? I have drawn an agenda for each day of how I would solve anything in 5 days. The first part is preparation. Sometimes when I work on performance, it can take weeks before we even begin analysis. This must be done before Monday. This includes installing critical analysis tools, like Linux Systat if you're on Linux, so that the tools are available to use. It involves fixing stack traces and symbols, so that you can look at the software stack trace and symbol resolution for software. I recently worked with the Ubuntu and Fedora communities to have that fixed in their default operating systems, so that stack tracing does work out of the box for Ubuntu 24.04 and for the latest Fedora. Tracing options must work, must be enabled, must be available. If you're in containers, if you're in Kubernetes, there can be various settings to make sure eBPF works and tracing works. The performance engineers must have SSH root access to the systems. Nowadays, that can be difficult. Many companies are disabling SSH. As SREs, you understand you need SSH access. You need to be able to log in. As a performance engineer, I do as well. A functional diagram of the system must be known. I have a diagram of the Apollo Lunar Module Guidance Computer. Having a diagram, a picture, helps you understand performance. You can look around for where issues can be. And you can measure every component on the diagram and every bus, every interconnect. And source code should be available. I've got a list of crisis tools. I put that in my book. And there's no time in a performance issue to run apt-get update, apt-get install. These need to be there beforehand. This is the preparation. Ubuntu did add these in 24.04. So that's the first step, is preparing the system for fast analysis. On Monday, the first things to check for a performance issue is quantify the problem statement method. This comes from my time at Sun Microsystems, where we would solve performance problems on the phone without logging in. With the problem statement method, you ask questions like, what makes you think there is a performance problem? Has the system ever performed well? Many times I've been asked to fix performance, and the database team or the web team has told me, performance is bad, please fix it. And I'm looking for a change. What changed? Nothing changed. Performance has always been bad. They never told me that. So I always ask, has it ever performed well? Then what changed recently? Software, hardware? Can the problem be expressed in terms of latency or runtime? Sometimes people will say, here's a performance issue, because it is a metric they don't understand has changed. But there is no performance issue. So I go through those questions and solve some issues straight away without even logging in, without looking at a dashboard, without SSH, just by asking those questions. The second task on Monday is static performance tuning. That's where you can check a system without load. Check all the hardware, software versions, past errors, config. I go through this in my systems performance book, which I should mention is on sale in the bookstore here at SRE Next. So I go through static performance tuning. That's useful for systems where the load has been turned off because the system was performing badly. I can still look at the system. And then finally, load versus implementation. Is it just a problem of load? At Netflix, there were I was SRE on call for 18 months. And I was woken up at 4 a.m. and odd times to solve the issue. And one thing we would do is look at social and the news websites to see if there was a sports game happening. Because sometimes if there was, say, a soccer game, when the other team would kick the winning goal, the fans of the losing team would get upset, turn off soccer, and then turn on Netflix. And so Netflix would see a huge increase in traffic, and that would cause a performance issue. And so I remembered to check, is it just load? Is there some sports final game? And that's solved using basic monitoring and line charts. I'm sure you can all solve this. I've got an example. That's an example daily graph from Netflix. So for the Monday activities, we are generally good at this. At the end of the day on Monday, if the problem is still unsolved, we know it's a real issue of this magnitude, as we've quantified it, affecting these systems. It is not just configuration, and it is not just load. On Tuesday, I would start with a recent issue checklist. Various companies I worked at have done this as well. Sun Microsystems used to do this, where the field engineers would have a checklist of top issues to solve. At Netflix, we would create custom dashboards, so the SREs could bring up a dashboard of recent issue metrics to see if it was the same thing. So back 20 years ago, this was more of a paper list, but nowadays it's more of a dashboard where you're checking for those top issues. Then, if it is not a top issue, I would say the next step is elimination, to figure out subsystems it isn't. It is too hard and too time-consuming to do a deep dive on everything in 5 days, in 1 week. We need to narrow down the search. We need dashboards that show health traffic lights, so you can ignore the healthy parts and look at the problem parts. We need new tools to do this that exonerate components. Apart from observing components, we can also do an experimental test, run micro benchmarks. eBPF is a relatively new kernel technology. It's in Linux, and Microsoft are working on adding it to Windows. And that has helped me create many new performance tools. And you can use them on a system without rebooting, without running in a special debug mode. You can use them immediately. eBPF will help us power. There are many of my prior tools I've drawn on that diagram. They include things like BIO snoop or exec snoop, the top tools, stat, count, slower. They're useful for following methodologies where I'm doing workload characterization, I'm doing latency analysis, off-CPU analysis, the use method. The new methodology I'm working on is Fast by Friday, and we need new tools. We need tools, I'd call them BIO health or memory diagnosis. They need to make it fast and easy. They need to tell the user, is that component okay? Or does it have an issue? Is there a possible issue? Is it unknown? Or is there a problem with the tool? Once we have these eBPF tools for all components that can show the health or diagnosis, we can create a dashboard to automate running them at your environment. And then you'll see green for most of your system, and then the red problem for some parts, or orange. So these new tools need to analyze the existing workload, and they should be open source and in the target code repository. My idea is these are like unit tests or code tests. So you develop the health tool. If it's a Linux health tool, that tool goes into the Linux source code next to the tests. If it is a Ruby tool, it goes into the Ruby source code next to the tests, or Python, or anything. Ideally, you get the original developers to help create these tools. They're very hard to do. I've written software components. It's very hard to think about being certain that it is okay, or it has an issue, or it is a possible issue. But these are the new tools that we need to create. At the end of day on Tuesday, if the problem is still unsolved, we know it's not a recent issue, and it is caused by these few components. We have narrowed our search. On Wednesday, profiling. Profiling has solved many issues. My flame graphs are very popular. Hands up if you use flame graphs. Wow, that's great. I've got 80% of the room. Awesome. Thank you. Flame graphs. CPU flame graphs, great at showing the code and showing you the code path that matters. There is also off-CPU flame graphs. These show when you are blocking on I/O, waiting on the scheduler or any other events on locks, and it shows you why. So CPU plus off-CPU, you have a software-based view of everything. At Intel, I've recently been working on AI flame graphs and GPU flame graphs. And so on the right, I've got an example of PyTorch. We recently open sourced the tools to do this. Only works on Intel, however. It doesn't work on NVIDIA. My tool does not work on NVIDIA. But that's what happens when I work at Intel. But we did open source it, so it is open source. That will be useful as well. So you can see the CPU, the AI flame graph shows the execution on the hardware, and then it shows the CPU stack that issued the GPU kernels or AI kernels. So you see the full big picture. These are great. They actually solve many performance issues, far more than my eBPF tools. So my eBPF tools, I like my eBPF tools, but flame graphs solve many more issues. Needs preparation, needs the stack traces and symbols. If the problem is still unsolved on Wednesday, we now know it's caused by these code paths. It should highlight the code path that is on CPU, that is blocking, or is on the GPU or AI accelerator. On Thursday, That's when I'd look at latency, logs, and critical path analysis. This is where things get more difficult. Latency drill downs. Latency histograms showing the distribution of latency. Many of my tools print that, like the BioDist and other ones, file system distribution tools. Latency heat maps. I have a heat map on the right that shows latency on the y-axis and the passage of time on the x-axis, and I quantize latency events and then use color, saturation as a dimension. That heat map shows a bimodal distribution. So I see a faster mode and a slower mode. And I see these vertical lines every 5 seconds. This is a file system. It's doing flush. And I can see a faster and slower events. Logs and event tracing. Many of my tools, my Snoop tools, print out logs that you can analyze. And then there's critical path analysis. Critical path analysis, it's supported by some tools. That's where you are looking at all of the connections within your environment or within loading a website or whatever, and which latency is slowing it down. It ends up being the critical path. Because you can look at a lot of latencies on a system and it's asynchronous. It happens in the background. It doesn't affect the client or end user performance. So critical path analysis lets you focus on the latencies that matter. At this point, the industry is not so good at this, so these are starting to get advanced. Critical path analysis, there is some tools for it, but usually it's a lot of work. So I've got eBPF tools for latency histograms and heat maps, latency outliers. I've got my Snoop BPF trace tools for doing custom event logs. These are all open source. They currently work on Linux, but they hopefully will work on Windows when we get the eBPF into the Windows kernel. And I also mentioned there is, for distributed tracing, there is a new ecosystem of zero instrumentation tools. They're using eBPF and uprobes, their user space dynamic instrumentation, to instrument library and API calls without having to change the software. I think it's a good idea if we make uprobes go faster. We still need to make uprobes go faster. They're a little slow, and so the overhead is a little high. And so I don't want people to think it's a bad idea until we fix uprobe speed. It's a good idea. We need to fix uprobes. If you haven't solved the issue by the end of day on Thursday, then you know that the distribution of latency looks like this over time. You know about latency outliers, which are very important. You also know latency is coming from this specific component. On Friday, efficiency, algorithms. When I learned computer engineering at university, I learned about the order of algorithm performance, n squared, n log n, how you can plot it. Changes to code for efficiency can have the biggest performance wins. Being able to change a cache lookup or a routine. However, I've said the industry status of this is 1 out of 5. We are not very good at this. There are many environments, customer environments, where we don't know how efficient our code is. How efficient is your code? Is it really good or is it bad? Like, how would you know? There is not a tool that measures efficiency of your code. So we have to look at the code, read it, look at flame graphs to try and understand it. When I worked at Sun Microsystems, I once did an exercise on a storage product that supported different file system protocols. It supported CIFS, iSCSI, FTP, NFS. I was able to micro-benchmark the same workload for those different protocols. And I could see how much CPU cycles each protocol used for a 1 kilobyte read. And I've drawn that table, and I could see that NFS version 3 used 395,000 cycles per operation, whereas CIFS used 2.2 thousand, actually over 2 million cycles per 1K read. That immediately tells you that the CIFS protocol is inefficient, and the NFS v3 is efficient, relative. In your environments at work, you don't have this table. You only know one value, so you've got nothing to compare it to. So that's the problem. How would you be able to compare your efficiency with nothing to compare it with? I would love a tool that could measure it and tell you how efficient it is. You could give it CIFS and it would tell you this should be 8 times faster. But that tool does not exist. So I think this is a largely unsolved problem. And in the future, it's not just cycles per request, but we also want to measure carbon per request. We can create new tools for this, very difficult. And system efficiency equals the least efficient component on the system. The outcome of this is to use faster algorithms. At the end on Friday, if the issue is still unsolved, there shouldn't be a problem. We've checked everything. We should be done. Following up from that, we can do a case study and retrospective. I think it's important when you solve performance issues to share them, especially sharing them publicly if you can. In the US, it is the norm to have performance engineering teams. Netflix has a performance engineering team. Many of the companies do have, I know LinkedIn and others, Salesforce have significant people doing performance engineering. And some of that is word of mouth. So people know that this is an important area to have staff. But in other countries, like in Australia, there's not really performance engineering teams. In Australia, there's performance testers, where people will run load testers and generate slides showing the results. I think what we need to do is share more case studies of why a performance engineering team is valuable, what sort of wins and money they save. So try to share things, external blog posts if you can, and in a retrospective, think about how would we debug it faster. So we're okay at some of this, we're not okay at efficiency and algorithms. There's room to improve. What needs to change? Performance wins that took weeks or months, we should find out how to improve that with better tooling, better methodologies. We need new tracing tools for health or diagnosis or exonerating components. Open source. In the code next to the tests, written by the developers. In the beginning, we'll make heavy use of eBPF and perf and ftrace. Later on, they may be built into the code. Crisis tools should be installed by default, like the sysstat tools on Linux, and we did get that fixed in Ubuntu. Frame pointers should be compiled by default. That's the quickest way we're going to do stack walking right now. There are some future technologies, like shadow stacks from Intel, that may help in years to come. But frame pointers by default, and I did help get that fixed in Fedora and Ubuntu. So to summarize Fast by Friday, this is Fast by Friday on one slide, what I think we can do, the activities. Any computer performance issue reported on Monday should be solved by Friday or sooner. And I think for SREs, once we've done this work and we have new tools and methodologies, we can then turn them into dashboards so we can try fast by 5 minutes. As a performance engineer, I can spend a week on an issue. As SREs, you can't spend a week. You need to solve this in 5 minutes. I've said solve a lot, but what I'm talking about is identifying where the problem is, the root cause. It's not fixed by Friday. That would be a different talk. And the best methodology I've heard for fixed by Friday are some mantras that I believe were published a long time ago by Craig Hansen and Pat Crane. And I've summarized it here. These are the performance mantras. This is about fixing an issue. Number 1 is don't do it, which means eliminate unnecessary work. Delete the code if it doesn't need to be done. That's my biggest performance wins. Number 2, do it, but don't do it again. That means caching. You do it once, you cache it. 3, do it less. So aggregate I/O, small I/O into big I/O. 4, do it later. Asynchronous I/O, background writes. Same as 5, do it when they're not looking, or changing like when you're doing backups, doing it in the middle of the night, do it concurrently, and finally do it cheaper. So that's a nice summary of how do you fix a performance issue, the different activities. Other takeaways, kernel superpowers, especially eBPF, are essential for fast in-situ production analysis. Fast by Friday, I think the time is right to create these tools because complexity is so difficult these days, and we have eBPF that lets us do live tools. If I tried to do Fast by Friday 20 years ago, it would be an academic exercise. It would go nowhere. It would be a thought experiment. But now, we can think about it and we can create those eBPF tools and use them in production. And we need them. We need them because things are too complicated. I'm not doing this alone. All of us need to get involved. It'll take us many years to do operating system changes, kernel support, new tools and methodologies. One step at a time. I've made some little steps with changing some operating system defaults, but there's a lot of things to do. And this will be the groundwork for Fast by 5 minutes. All of the tools and methodologies hopefully will be summarized by a dashboard. I can imagine what will happen is there'll be many startups will be selling this as a dashboard, and those startups will get rich and I will not. But that's the way it works. They'll be selling Fast by 5 minutes as a product, a software service. Now, you can talk to me. There is a Meet the Speaker section, and I'm also doing autographs since I see my Systems Performance book, 2nd edition, has now been released. And so 12:30 to 12:55 in the same area. And that is my keynote. Thank you very much to the SRE Next organizers. And also, you can see Sohei Arihori-san's talk tomorrow on SRE and eBPF. So thank you very much.